Susan, how are we doing today? Hey, Roxy, how are you? Hey-o. Oh, I better go to the other camera. Go to the other camera here. Woo! Hello! Doing alright, Susan? Wonderful. I'm doing great. Today is a wonderful day. A wonderful, 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 wonderful day. As always. But today is a good day because I get to come on here and have a fun time. I don't see a problem with any of this. Haha! Roxy, I see you were in a chipper mood earlier. I'm really happy to see you in a chipper mood today. Overall, smiles in the whole 9 yards. I can run with that all day. 1000%. Turn this down just a smidge. There we go. Perfecto. Woo! Wow. It's already getting to be nighttime over here. Man, that was quick. But it has been already a wonderful day. It's been already a busy day, to be honest with you guys. Very busy. But I got stuff done. I got glowing reviews. Alright? Ty Hawkins, my friend, how are you? How are you doing today? Are you doing okay? Holly, hello, hello. How are you doing today? Gemma, 11:59 in the UK. I'm just popping to say hi and have a fantastic day. Gemma, I hope you are having a fantastic night. I hope that you will rest well and have a wonderful, wonderful, not only 1 minute of the rest of that day, but the other subsequent 24 hours after that as well, if I don't get a chance to talk to you before then. I hope you have a wonderful time. So, I know, isn't it? I had a meeting with the boss today and everything, and the boss had said that she really liked Twitch and us conducting classes on Twitch, and I was super happy with that, so I'm in a good mood there. I know. So I'm hoping that the next 24 hours there, Gemma, are just as good as the minute that just has passed. There you go. We're all good. Man, look at this. It's 6 o'clock here in the United States of America. It's the evening time. I've had some Chipotle. Okay, it's been pretty good. Thank you, Ty. I really appreciate it, my friend. Hey, I hope you have a wonderful night as well, Ty. Much love to you and the 2Sync fam, alright? I hope you are having a wonderful day. Yeah, see? Positive vibes, everybody. Positive vibes. Woo! Alright? Positive vibes. At least, I was a little salty playing some code names, but no longer salty about that. We're gonna move on to better things. And you're like, Ah, yes, look at this here. Doing good today. Yeah. Connor, hello. We're gonna wait for a few more people to come on in. We'll get started here. We'll start just a couple minutes late, but just want to wait for a couple more people to come on in, then we'll get going. Okay, bueno. Yes, by the way, drink of the day, ladies and gentlemen. Drink of the day. I've drank this since the afternoon, but it's still outstanding. It is today's drink of the day. All right, Gemma, you have a great one. I got Mitsuya cider. This stream is brought. This This whole day is brought to you by Mitsuya Cider. Okay, it's a nice sugary pop drink. Okay, absolutely outstanding. All right. It's a soda drink that's called Mitsuya Cider. So it kind of has that cider taste to it, but it's really a soda drink. So, and no, not alcoholic cider, mind you. I do not drink alcohol on stream, so. That's a Japanese drink, Mitsuya Cider, so very good. Very delicious. All right. I think we're ready to get going here, ladies and gentlemen. So let's get going here. Let's do some things here today. We got work we gotta do here. Let's do it. Smuggled into the U.S. of A. Too true. All right, let's do this. Okay, let's get started today. Welcome back. Welcome back to Wednesday. Wednesday, end of the week time today. So today we're going to continue on with Chapter 6. Am I a hashtag United fan too? You betcha I am. My dude, I'm a huge hashtag fan. Absolutely crazy big hashtag United fan. So, I love hashtag United. So, trust me, they'll know. All right, Natty, good afternoon / evening / whatever you want to call it here. Thank you very much. Hey, and how's it going, Natty? I hope you're doing well. So today, ladies and gentlemen, we're going to be moving on here into the next chapter of the textbook. Today, we're going to be doing Chapter 6. Now, when I say we're doing Chapter 6, Chapter 6 only has 2 sections, okay? So we're only going to be doing all of Chapter 6 because there's only 2 sections at the end of the day, and there's not, we'll be able to get through both handouts here. Again, you probably have a combined handout. I have a handout here from before because, again, it shares the book with 102. But the answers to the questions here are pretty much exactly the same. So we're going to answer our questions here via our handout, and we're going to get going here. We're going to hopefully get this done. That's the way I'm doing things, question mark? Okay, sure. All right, let's learn some stuff here. Let's do it. All right, let's go. Let me actually go here for a moment. Here. Textbook. One thing I always forget is to post up the textbook here. Oh man, holy smokes, the textbook. Come here, Mr. The textbook. I'll put this onto the main screen here. Let's go. Big board. Big board time. All right, let's see where this see where section 6.1 is off the top of my head. It is on 316 here. So all right, perfect. Exactly where I want to be. Okay. All righty. So today, we're going to be doing a couple of things. Let's go ahead and go over to the handout here for today from section 6.1. Today, we're going to be talking about, in section 6.1 anyway, we're going to be talking about discrete and continuous random variables. So we're going to talk about random variables and what they are, and of course, discrete and continuous. So this will be something that we talked about before back in chapter 1. We'll talk about how to do the mean / expected value, and we'll also talk about the standard deviation and variance from that as well. Natty, I'm doing good. I'm doing good. We're doing good today. Yeah. All right. Let's go ahead and talk about this here. Let's look at question number 1. All right. So question 1 says, what does question 1 say? Question 1 says, what is a random variable? So what exactly is a random variable? So a random variable is a numerical measure of the outcome of a probability experiment, so its value is determined by chance. Okay, and so what do we use as a random variable here? A random variable here is listed as the letter X, okay? It can be literally any capital letter, but that letter X just represents one outcome of any particular experiment. Now, what we are trying to do is we're trying to put all the probabilities into one table, Okay, so it's like, okay, if this is the outcome, this is the probability associated with this outcome. If this is the next outcome, this is the next probability associated with that outcome. All right, so what we want to do is just, again, arrange it in a way where it's easier to kind of look at a list of probabilities here and then start doing some computations with them. That's primarily what we're looking in here for section 6.1. Now, in what context are we looking that over? Well, let's take a look here at number 2. Actually, before we do that, again, it's the same thing as if I said instead of X, I said rolling a 1, like the probability of rolling a 1, for example, and I would assign the capital X to be rolling a 1. I could assign capital Y to be rolling a 2 or whatever. But you get the general idea. It's really not too hard if you try to put it together. I like writing it in because it's a lot easier to do, but if we're just doing it all at once, then a variable is just fine. Okay, in any case, we'll look at an example here shortly. Okay, let's look at numbers 2 and 3. Now, numbers 2 and 3 here, if you remember, we talked all the way back in chapter 1. All the way back in chapter 1, we talked about the discrete and continuous variables. And if we talk about a discrete random variable or a continuous random variable, those definitions that we talked about back in chapter 1 a long time ago, those guys aren't going to change. So as you see here, what's a discrete random variable? That's just a random variable that has a finite or countable number of values. Just the same definition we talked about in chapter 1. What's a continuous random variable? It's a random variable that has an infinite amount of values. So that's just, again, same definition as chapter 1. The only difference here is that you can graph these particular probability distributions. So if it's discrete, you could put them as points on a graph, for example. Or if it's continuous, you could put it as a line since it can take any value in between, say, say 0 and 100 on a test, or if it's continuous, if you had like decimal scores down to the fraction or whatever. So whatever. It could be literally anything. All right. Okay. Now, let's talk about a probability distribution. So what is a probability distribution? A probability distribution is a distribution that represents possible values of random variables and their corresponding probabilities. Now, what we're talking about here is that essentially we're just taking a look, like we had a frequency distribution, we're just looking at a probability distribution. Okay, that's all we're looking at here, just probability distributions, simple enough as it is. So what we need to recognize is that the two things associated with that here, with a probability distribution, is that the same two properties are going to hold true. So for example here, letter A says the sum of all the probabilities are going to equal 1. So if we add all the probabilities, just like we talked about in chapter 5, okay, all the probabilities, if we add it up together, that's always going to equal 1. So that's fine. And the probabilities, no matter what they have to be, they always have to be between 0 and 1. So it has to be 0 or 1 included, or anything else in between. All right, so those parts there, no different than what we talked about before. Pretty much exactly the same properties that we had from before. We're not treating it anything differently here. So let's take a look at number 5 here. Number 5 says, how do we find the mean/expected value of a discrete random variable? Now, let's go ahead and talk about this guy here, because this is really the big meat and potatoes of what we're talking about here in this section, is talking about the mean/expected value. Now, as you can see there are two notations here to kind of go along with this. There's this mu of x, and then there's this e of x. So mu of x is like a mean, e of x would represent expected value. And that's equal to this guy here, which represents the sum of all, whatever the value of the random variable is, times its respective probability. Okay, that's essentially, and we're just going to add all those guys up together to find our expected value. So really the big thing about this is calculating the expected value, or calculating the mean here in a probability distribution. It isn't that hard. Really the important part here is what it means, because it does have a grander meaning than maybe just its kind of mundane look. So let's take a look at an example here, and we'll go ahead and work with this here, and we'll see exactly what we have here. 1 plus 1 equals 2. That's my math's done for today. I'm sorry, but that is the wrong answer, Connor. 1 plus 1 does not equal 2 in every case. So That's math for you. All right. I'm sorry, Connor, but that's not true for every case. All right, let's get the paint tool here. All right. So let's take a good look here, and let's look at all right. So the problem that we're going to specifically look at here in this case is we're going to look at number 18, and we'll answer some questions in relation to number 18 here. Okay? All right, so let's give it a go. Number 18. In the following probability distribution, so this is what a probability distribution looks like here, like you see in number 18. The random variable x represents the number of marriages an individual aged 15 years or older has been involved in. So here, what you see here in the list is that here you see 0. Now 0 represents, again, 0 marriages according to the context of this problem. And what's the probability that that person will have 0 marriages? Okay, here's our probability. 1 marriage, here's our probability to go with that. What about 2? Okay, there's our probability to go with that. What about 3? There's our probability to go with that. And so on and so forth. Okay, so this is essentially your x and your probability of x. Not too hard. Now we want to answer several questions that kind of go along with this. So let's at least talk about that. First and foremost here, look at the first part that I want to talk about. Let's find the mean/expected value. Okay, so if we want to find the mean/expected value here, we go back to our formula here for just a second. That one. That we're going to do later. Again, we're going to take x, whatever x is given to us here, and we'll multiply it by its respective probability. We'll just go straight across, and we'll just go ahead and add all those results there together, and we'll find our mean/expected value here. So if we're going to find it here, we'll do e of x equals 0 times 0.272 plus 1 times 0.575 plus 2 times 0.121. All right, plus 3 times 0.027. All right, plus 4 times 0.004. And then plus 5 times 0.001. Okay. So if we add up all these numbers together, can anybody tell me here? If we take all these guys together, let's you can get out your calculator for this one here. But if we took all these guys together here and we added it up together, what would we get here in this case? What do we get here after adding these up together? Put that in the chat there. I'll go ahead and wait for you guys to get this going here. So Okay, got a couple of answers there. 0.919, 0.7012. Remember, this is 2, 3, and 4 here. It's 2 times 0.121. So 0.917, that's close. I'm going to go with one of those answers is correct. So I'm going to go with one of these answers is correct here, and that's going to be 0.919. So 0.919 here would be the correct answer here for this particular instance here. Okay, now make sure you enter that in correctly in the calculator. If you didn't get the correct answer there, just make sure you get those numbers down. Now, to be fair though, there are a lot of numbers floating around. So I'm just going to point that out there and be like, yeah, you know what? There are a lot of numbers floating around. So you didn't get it right the first time, that's fine. Well, I'll showcase the short way to do this. In any case, the important point here that I do want to make specifically is what 0.919 represents. Okay? Yeah, if you missed a number, so that could very well be the case. So I want to point out one thing here. Oh, okay, that's what happened. So I want to point out one important thing here. What does 0.919 represent? Because this is the important part here about expected value. If we want to expand and talk about expected value as an actual meaning, then this is actually the real life application of why this is so important. So this basically says is that uh, there, I should say this, there is on average 0.919 marriages. I should probably make that smaller. Not like that. That wasn't. All right, there is on average 0.919 marriages for people 15 plus. All right, over their lifetime. Okay, so there's on average 0.919 marriages for people 15 plus over their lifetime. All right, according to this probability distribution, that's how it's going to go out. So if you looked at it from a long-term perspective, you're going to have, close to, on average, 0.919 marriages. Now, realistically, of course, there's no such thing as a 0.9 of a marriage, unless you're like a celebrity and you just kind of half-ass it. I mean that could be a thing. I don't know. Just saying. But in this case here, it's close to about one, having one marriage over your lifetime there. That's what you have on average. Okay, so according to whatever this probability chart is, this instance. So we're going to look at another example where we'll see how that can greatly affect things if you look a little bit toward the future. Okay. Are there any questions about that so far? Any questions? Any questions so far about that? All right. Let's talk about the next part here. Let's talk about the next part here. All right. So the next part here that we're going to talk about for this particular problem anyway, is we're going to try and find the standard deviation and the variance. So let's talk about that here. Now let me showcase off here the standard deviation, at least the formula here for the standard deviation. So if we talk about the standard deviation, this is the formula here for the standard deviation. So how do we find the variance and standard deviation of a discrete random variable? Well, here's the formula associated with the variance and standard deviation of a discrete random variable. Now, I'm going to preface this by saying this, okay? Although you see this on the screen, on the right-hand side of the screen, okay, I'm not going to make you memorize this formula, okay? This formula is not made to be memorized, okay? Instead, what we are going to do is we're going to take a nice shortcut method here, and we're going to go ahead and see what we see how we can come up with this using our calculator. Okay, so don't worry, you don't need to memorize this or use this. Again, doing it by hand for standard deviation, as you can probably tell, would take a little bit of time to do. So really want to do that here in this instance. Okay, so let's take out the calculator and let's see what we're working with. Okay. All right. All right. Okay. So what we're going to do here first is we're going to go ahead and put this in the calculator. If you have your calculator out, let's go ahead and get that out right now. Okay. And let's go ahead and get started here. Let's go ahead and hit the let's hit the stat key here. Let's hit the stat key. Gonna go over to calc. Oh, and we're going to calc. I'm sorry. We're gonna go to edit. Sorry, my fault. I gotta enter in the data first. So we're just gonna clear out this stuff here. So hit clear and enter. If you got stuff already in there, we'll hit clear and enter. Okay. Just clear out those lists just like so. Okay, now in list 1 here, we want to put down all the possibilities for x. Okay, so that's all that will go here in list number 1. So we're going to hit 0, 1, 2, 3, 4, 5. And here in list number 2, we're going to put in all the probabilities that we were given here in this problem. So 0.272, 0.575, 7, 4. All right. So these are the numbers that we should put in here into our lists. Once you guys have your numbers in your lists here, if you could type done in the chat. So please type done in the chat once you have your lists in your calculator. And he's done. All right. Wait for other people to get done. Make sure that this is on their calculator. All right, Susan's done there. Okay. All right. All right. Anybody else need help with the calculator? I'll wait and see if anybody else needs some help. Otherwise, I will move forward. Okay. We will move on then if nobody needs any more help. Okay. So what we're going to do next here is we're going to go ahead and hit the second key here and hit the mode key. We'll quit out to the main screen. So that way we avoid entering anything bad in. So we don't want any bad data floating around. All right, so we'll hit the stat key here once again. We're going to go to calc, and we're going to once again go to 1var stats. So we're going to go to 1var stats here. And again, if you have an old school calculator, If you have an old school calculator, then what you want to enter in is L1, comma L2, so you want it to look just like that. Or if you have this submenu here, you'll see list number 1 put there. We do want a frequency list here as well, so if there's a blank in there, for example, just go ahead and hit second and the 2 key, and then list number 2 should show up, and you go ahead and hit calculate. Okay. All right. And once again here, I'm going to ask everybody who's in chat there to type out done if this is the exact screen that you got. If you match this exact screen here, go ahead and type done in the chat. Okay. All right. Okay. So let's take a look at what we have here on the screen. What we have here on the screen is we have the mean here, or the expected value, which is 0.919, and we have and what we have here, more importantly, outside of that, now that we've confirmed the mean here anyway, is we also have the standard deviation. And the standard deviation here is given to us as 0.7392. So that's fine. Okay, so that's our standard deviation that we can find here directly via the calculator. Now, one other question I got from the very first exam is how would we figure out what the variance is, for example, like in cases like this, because we're given just the standard deviation here. Now remember that the variance here is just the standard deviation, and you just take that number and you square it. So for example, if you're doing the My Math Lab stuff, what they expect for you to do for the variance here, and I'll show you with this example, what they want you to do for the variance here is they want you to take this number all the way out. Okay, so just take this number all the way out. So 0.7392151243, and we're just going to square that number straight up. Whatever we get for this number here, it's going to be our final answer for our variance. So our final result here for our variance here will be 0.5464. Okay, and that's how we can go ahead and find our variance for this. Seems okay. All right. Yeah. Okay, any questions about that? Any questions at all? All right. Okay. All right. So that's how we can do that question, at least for those first two parts. Now, I do have one more part here that I would like to do for this particular example. So this kind of talks, this last example here, or last part, talks about something that we discussed here back in chapter 5. So let's do this last part here. And we're going to go ahead and have the book over here to help ourselves out. So we need it for this. All right, so what is the probability? So we can figure out probabilities here using this table. What's the probability of at least 2? What's the probability here of at least 2 according to our probability chart here? Probability of at least 2. What What do you think that's going to be here? Probability of at least 2. What exactly qualifies for at least 2? Point 817. 817. Oh, okay. I think I know how you got that. You have that a little bit backwards, I think. So, what does at least 2 mean, Beth? What exactly does at least 2 mean? Let's at least establish that fact there. What does at least 2 represent? The numbers leading up to 2? I think you have that backwards here. You're thinking of less than 2, but I'm saying yes, okay? So 2 and up means at least 2, okay? That's correct. Right. So at least 2 means 2 or more. So one of the things we talked about back in chapter 5 was how wording plays an important role in how we are actually going to be able to do some of these problems. All right? So if I were to look at this, at least 2 means it's the probability of the 2 case plus the probability of 3 plus the probability of 4 plus the probability of 5. Okay, so cases 2 to 5 here would represent at least 2, since that represents 2 or more. Not more than 2. More than 2 is different than that of 2 or more. Please be careful about that as well. So, if we have 2 through 5 here, we're just going to add up those probabilities since they're already listed in the table for us. All right. And so if we do put this together here, I believe 0.153. All right. Good stuff. Okay. Are there any questions about that? Any questions about that particular example? So again, the wording there, again, I know it's a little tricky, but once you get used to it, not too bad. All right. Perfectly fine. Perfectly fine, ladies. All right. Let's go ahead and do the next problem here. Now, this time here, I would like your participation for this one. So this is kind of like you got to try this now. Now that you know how to kind of do the last few parts here of this first example, hopefully we can see where this is applicable. Again, a real life example here. So one of the things where expected value is very important and where it's used is, say, the casino. The casino is a very good way to understand expected value. For example, how much do you expect to win in a given game of any variety on the casino floor? Okay, and this is basically assuming that if we had unlimited money with unlimited amount of plays, over the long term, how much are we expected to actually make in a game with the given rules that we have? In this case here, for number 27, this deals with blackjack. Okay, so as we know with blackjack here, you're trying to get 21, you're trying to beat the dealer. All right, you have to have if you beat the dealer, you're in great shape. Wonderful stuff. Okay, so again, here's the winnings. You can either push, which means neither of you win, so that's the probability for that. $30 means you get a blackjack. $20 you win 20 bucks means you beat the dealer, or you lose $20 for just sake of losing 20 bucks since you couldn't beat the dealer, and the probability that's associated with that. Now there's going to be two parts to this question here for number 27 that I'm going to ask you to do. Letter A, of course, is finding the expected value here for the blackjack game. All right. And letter B pretty much says if 1 hour equals 40 hands, how much do we win? How much do we win or lose? How much do we win or lose after 3 hours? Okay. So let's take 3 or 4 minutes here. I'm going to give you 3 or 4 minutes to try this problem out. We'll come back in 3 or 4 minutes. All right, and we will see exactly what we get here for parts A and B. So I'll put some music on here. Let's give it a try. You got it, buddy. I did. I just did. Tastes like victory. Too true, Connor. not so much of an equation here, Natty, as there is just kind of you have to use what you got for letter A on letter B. So see if you can use letter A to help yourself out for letter B. Yeah. I'll give you another minute or two to kind of think that one over. Thanks, Connor. You have a good night. All right. Okay. Alrighty. So we've had a few minutes here. Let's go ahead and go over each of these parts here together. You guys a little bit of time here. So what did we get here for letter A? What did we get here for letter A? What is the expected value of playing this type of blackjack game with these probabilities? What did you guys get? Ooh, all right. That is correct. Very good. That is correct. So negative 0.5 or negative 5 cents. That is the correct answer. Very good. Nicely done. Right? Because all you have to do here is take each one of these, right? You did multiplied each one of these guys. Okay, added it to 30 times 0.0483. Right? Add that to 20 times 0.389275. And then finally we get okay, and then put the last one here as plus minus 20 times 0.4642. Okay, and so if we added these all up together, I would totally agree. We would get negative 0.05. All right, so that was letter A. All right, nice work. Nice work, ladies. All right. So, what about letter B? If 1 hour is equal to 40 hands, how much do we win or lose after 3 hours? What did you ladies get here? What do we get here? We got negative 0.15. Not exactly. That's fine. That's fine. Here, I'll tell you what. It's fine. That's perfectly fine. It's good that you're confused here because, again, let's talk about that. I don't mind if you're confused. We're here for learning. So let's talk about what this means, right? Let's talk about the meaning here. What's the real meaning behind negative 0.05? It means for every hand of blackjack that is played, you lose 5 cents on average. If you played unlimited hands. So, if for every hand of blackjack that is played, you lose 5 cents on average if you played unlimited hands. So, it's a $20 game. These are the rules of the $20 game, okay? This is how much you make lose. And if you played unlimited hands, you had an unlimited amount of money, you had an unlimited amount of time, you're losing on average 5 cents a hand. Okay. So now with that interpretation in mind, what do you think here? What do you think that the answer is going to be here in this case? What do you think we'll get here in this instance? What do you think I should do here? I would multiply by 40, yes. Minus 6, yes, that is correct. Very good. That is correct. So, how did you get minus 6 there, Susan? I agree with the answer here. But let's talk about how we got to that result there. So, that would be very important. How did we get minus 6? Get minus 6 here. Okay, so you're losing $2 an hour, all right? All right, that works. Perfect. All right, so we could take negative 0.05, multiply that by 40. So for 1 hour, 1 hour's worth of winning or losing. In this case, we lose $2 an hour. Multiply that by 3, and we'll lose $6 for 120 hands or 3 hours worth of playing blackjack. Okay. Now you're probably saying, "Hey, I spent $20 a hand. It doesn't seem like a whole lot, to lose $6." Well, in reality, if you're playing a whole bunch of hands and you're losing $6, I mean, there could be times you go on hot streaks. There could be using on cold streaks. You could be middling somewhere in the middle. But at the end of the day, you're still losing more money than you're gaining. So that's what they always say, that the house always wins. Well, here's a way that the house always wins. Obviously, blackjack is one of the nicer games to actually go into a casino with and gamble. You have slightly better odds there, but yeah, the house still has odds in their favor, irrespective of that idea. The same thing applies for um, what's the worst game? The worst game in a casino, by the way, is roulette. Roulette is the worst game in the casino. So you will lose on average per game, instead of 5 cents per hand, every roll of the ball, you're destined to lose 26 cents to the dollar. Yes, 26 cents. So yeah. Roulette is the absolute worst game to ever play in the casino. You will get taken for a ride. Yeah, you like that game? Oh, I don't like that game. That game is bad. The game is just bad all around. Worst odds in the casino and doesn't pay very well. If you're ever going to play 2 games in the casino that are really good, you could play blackjack, of course, because you can kind of flip the odds in your favor if you count cards, though you don't want to get kicked out of the casino. Or poker. Poker is very good because you're usually playing against other players, not the casino. So yeah, those are 2 of the best ones that you could probably pick if you're going to play games in there. Okay. Okay, are there any questions about these two parts here, ladies? Any questions? Those are the two games I don't know how to play. Blackjack isn't that hard to learn. Poker can take some time, though. Okay. Now I'm going to ask you ladies here, do you want to take a break or do you want to continue moving forward? Or anybody else in the chat really? You guys let me know. What would you guys like to do? Continue? Okay. All right. Then let's go ahead and continue then. Alrighty. So that's essentially section 6.1. All right. So that's all of section 6.1. It talks about probability distribution and whatnot. So fine. That's done and dusted. All right. Let's talk about the second one then. The second section for today. Let's talk about the binomial distribution here in section 6.2. Now, I am going to preface this by saying this here. A lot in this particular section here in section 6.2 is going to rely on the calculator and getting to know how the calculator works. So we're going to talk about that here. I'm going to fill in a little bit more of the blanks in here to know exactly what this represents. Okay, so I'm going to point that out there, talk about it, see what we're working with. All right. In any case, what is the binomial distribution? What's the formula? There's a formula that goes along with this, and there it is. You see the formula there. It talks about the number of combinations. It talks about a p. It talks about a 1 minus p. It talks about an n minus x. It talks about a lot of these different things. Let's talk about what we can break down binomial distribution to, okay? Because there is scenarios where we can use this particular distribution. So where does this actually go into? Well, the only thing that we care about here in this section are two words, and they're on the screen, but let's talk about it here. The key here is to remember success and failure. The only way a binomial works is that, remember the word bi. Bi means two, like binary, ones and zeros on a computer or whatever. Okay? What we want to do in a binomial distribution is talk about what's considered a success and what's considered a failure, and how many of those things were successes and how many of those things were failures. Okay? So we want to talk about that there, right? Now, associated with the success and failure is, for example, the probability of that success, or on the opposite ends of the spectrum, the probability of failure. That's why you see here, for example, you see here that we have a few things that we have to take into account. First of all, p being the probability of success, and just the opposite here when we did like the rule of complements, 1 minus p or 100% minus p is going to be the probability of failure. We also have a number of trials, so we try a bunch of times. We have some number of successes, which we'll call R, and then we'll have the number of failures here, which we'll call n minus, should have been, this should have been R here. I don't know why I put X here. We change that up. All right. I'm going to switch that over a bit. R here. Yep. Accidentally X for that. There we are. Much better. Got that backward. All right. All right. All right. Now the issue, here's the problem, okay? Let me talk about the problem with this formula here. The problem with this formula is that we could end up with a lot of different cases. Okay? which means that we would have to do this calculation that amount of times. Kind of a pain. Okay, that could be very painful very quickly. So we're going to definitely use our calculator for this, but we're going to look at it in a slightly different way, maybe. Now, in this case here, I am going to put down a second key for this here, and we'll talk about number two. Number two, there's only two questions here, by the way. But we're going to talk about key number two here. Now, and I know you're not going to like this, but it is something that I've already talked about here. Wording is important. So one of the things that we talked about already is that wording is a thing. Wording is very important. We need to be very careful about how we actually write out certain things with the wording in the problem. Okay, we're going to look at this very carefully here. And we're going to see exactly how we can do the proper calculations with the wording in place. All right. Now, let's do it this way. Okay, now to understand the wording and how we do the calculations, let's talk about it this way. I want to go to our calculator here for just a moment, okay? Because what's on our calculator has several different meanings, okay? So let's talk about that here, because you're going to have to use the calculator and you have to use it properly here in this section in order to get this down. Okay. So the first thing that I'm going to do here is I'm going to go over to a very specific, we're going to look at two specific functions here on the calculator. Now to find these particular functions, we're going to go ahead and hit the second key. We'll hit the second key and we're going to hit the vars key. We're going to hit the second key and the vars key right here, and we're going to go get to this menu right here. Okay, so this is the distribution menu, because in this case, we're going to be talking about a binomial distribution. Now, I want you guys to scroll all the way to the bottom here, and we're going to look at two options here. This says Binomial Pdf, and we'll also look at the counterpart here, which is Binomial Cdf. And we're going to talk about both here because they both have different meanings. Okay? Let's first talk about Binomial Pdf first and foremost. Okay. So what's underneath Binomial Pdf? What's the formatting for that if you were to look at that carefully? Take a look. Binomial Pdf here, we have three numbers that we plug in here. We have, first of all, the number of trials. Oh, what did I do? Notes. Right? So we have the number of trials. That's the first number, comma, the probability of success. Okay? And then comma, the number of successes. Now, the important part about Binomial Pdf specifically is what it means. Binomial Pdf means exactly that number of successes. Okay? So Binomial Pdf means exactly that number of successes, all right? I want to be sure that you understand that exactly that number of successes. This is very important because it will dramatically shift the way we do certain calculations based on the wording of the problem. On the other hand, we have one more to talk about here. let's talk about that here as well. I'm going to hit the second and vars key here again. This time, though, I'm going to go to letter B here, which is Binomial Cdf. So what's the formatting here for Binomial Cdf is exactly the same as PDF. Okay, so number of trials, probability of success, and the number of successes. However, Binomial Cdf has a different meaning, a very specific different meaning. In this case here, Binomial Cdf represents the probability of, in this case, less than or equal to the less than or equal to that number of successes. Okay, this is really important. So we're limited in what each calculator function can do. Okay, we're very limited on what each calculator function can do. Binomial Pdf talks about exactly that number of successes, and Binomial Cdf talks about less than or equal to that number of successes. Okay, so we're going to have to make adjustments because these two functions are very specifically designed by the calculator here. Okay, so let's see exactly how this is going to work. Let's take a gander at an example in the textbook. All right, come back to that formula here. All right. All right. Let's take a good look here at number 37, one of the funnier problems here in 37. So let's take a look at this here, and let's see what we're working with, yeah? All right. Okay, so 37 says, we'll come back to the calculator in a second. 37 says toilet flushing. All right. So in the healthy hand washing survey conducted by the Bradley Corporation, it was found that 64% of adult Americans operate the flusher of toilets in public restrooms with their foot. Suppose that the random sample of n equals 20 adult Americans is obtained. The number. Do you guys flush with your foot in a public bathroom? Mood. you guys you guys do that in the public bathroom? You know, you flush with your foot. And you're like, yeah, I don't want to touch that. Yeah, of course. Oh, okay. I know that seems gross, but I just kind of I don't. I wash my hands very vigorously. I wash my hands very vigorously in the sink. But I just flush it straight and be like, all right, let's just wash my hands. So gotta disclaimer. disclaimer. Disclaimer, I might be grosser than other people, but I promise I do clean up. I always wash my hands afterwards. So yeah, especially with COVID, I can totally understand that. All right. So suppose we took a random sample of 20 people who flushed public toilets with their foot is recorded. Okay. So let's look at letter B there. Find and interpret the probability that exactly 12 flush publicly with their foot. All right. Probability of exactly 12. Okay, so let's answer this question here. Are we going to use Binomial Pdf or are we going to use Binomial Cdf? Use PDF or CDF? PDF or CDF here? Let's go back to our handout here. PDF or CDF? Natty, what do you think, Natty? All right. So in this case here, we're going to go ahead and use PDF. Okay, so we're going to use Binomial Pdf because it says it's exactly that number of successes. So the question is, what are we going to put here using Binomial Pdf? Go ahead and put this down here. Now, if we follow along here, right, the numbers we're going to put in specifically here are going to reference first the number of trials. How many trials do we have here? How many trials do we have here? How many people were in this experiment, according to what we have here? What's our number of trials? What's the first number there? 20, correct. So 20 is going to be the number of trials, okay? Then we have the probability of success. So let's go back to our guy here. We have the probability of success. That has to be the second number there. So according to the problem here, what is the probability of success? What should we put there for the second number, the probability of success according to number 37? What's that going to be there? What's that probability of success? What do you guys think? Hmm, 12? Well, can't be 12 because 12 is more than 1. Remember, probability has to be between 0 and 1. 0.6. Not quite, but close. 0.64. All right, that's correct, Natty. Right. So the answer here is 0.64. Notice here it says 64% of adult Americans operate with their foot. So this is our probability of success here. In general, 64% use their foot. So that's fair. All right. So we have to have the probability of success here being 0.64. All right. Okay. That's why we're doing this one step at a time here. Let's take a look at the last part here. The last part here is the number of successes. So what is the number of successes here? What's our number of successes according to this problem? 12, right. Now, to make things less confusing for you guys, I'm going to go ahead and say this as a note here, because it seems to be a sticking point for whatever reason, semester by semester, but I think it's at least important to make this note here, so I will. Okay. Let me put a note here. Note, the first number is always bigger than the third number. Okay? I'm going to point this out here because that happens to be a point of contention. Sometimes people get 0 as their probability when they do this out, but this always happens in the binomial distribution. The first number should always be bigger than the third number because the first number represents the number of trials, the third number represents the number of successes. All right, but just to be on the safe side, I'm going to go ahead and put that as a note there. That way you don't forget when you're trying practice problems out. All right, now let's go ahead and put this in the calculator. See what we get, right? Why not? Got a calculator? Let's use it. All right. All right, so again, to get to that point here in the calculator, let me go ahead and quit to the main screen here real quick. To get to that in the calculator here, hit the second key, hit the vars key, V-A-R-S for vars. Going to scroll to letter A for Binomial Pdf in this case. Put in our number of trials here, which was 20. Probability of success, which is 0.64. And our number of successes here, which was 12. And we'll go ahead and hit paste. Hit enter. And there we are. We have our final result here. Our final answer here is going to be 0.1678. Okay, good. Questions about that one? Any questions so far? Yep. All right. Hopefully that made it a bit easier to kind of digest. All right. Let's look at, no, all right. Holly's back. All right, there we go. All right. So let's look at letter C. Letter C, according to the book here, I'll just go ahead and read this off here. Find and interpret the probability that at least 16 flush with their foot. So probability of at least 16. Okay. Probability of at least 16. All right. Let's go here for a second. So, go back to our handout here. So, let's answer this question again. Which one are we going to use? Are we going to use Binomial Pdf or Cdf? Time. Using PDF or CDF? PDF or CDF this. Okay. All right. That is correct. All right. Very good. The answer is indeed CDF. Okay. Again, because now we're adding up a number of successes here, because we're talking about at least 16, right? Talking about at least 16. Okay. We need to be a bit careful about this here. We need to at least we need to put this in a proper format. So let's go ahead and it's down here. How can we represent at least 16? How can we represent that using Binomial Cdf? Put Binomial Cdf. What numbers should we put here for Binomial Cdf to represent the number of successes? Let's at least put in some numbers here. What should this first number be for Binomial Cdf? What do you think I should put there? Binomial Cdf, and then what should our number of trials be? What do you guys think? All right, 20. All right, so that part's not going to change. We have 20 here by default. I'll fill in the probability of success. That part is still 0.64. So 0.64, 20, 20, comma 0.64, that's fine. All right. What should we put here as our last number? What should we put here as our last number? What do you think here? What should we put here as our last number? 16. That's pretty close. Not quite here in this case. That's pretty close. Very close, Beth. Very close. But I can understand that the first thing you want to put is 16 here, right? Not quite the case here in this instance. Give you guys another guess here. That's fine. This is a tricky question, so if you don't get this, I'm not going to blame you. It's just, I just want to see if you guys can see it a little bit further ahead. So, 17. Ooh, not quite 17. 15. I will go with 15. Yes, 15 is the correct answer. I'm going to go with 15 right here. Now, I am missing something else as part of the 15 here. Now, you're probably not sure. Yeah, that's fine. That's fine. 15 is the correct answer. And you're probably like saying, whoa, whoa, whoa. Time out. Time out, Professor Chibs. That doesn't make any sense. Why the heck would you put 15 there? You know, we have at least 16. So you're saying 15 works in this particular problem. You're like, huh? How does that work? Well, let's take a look at why 15 needs to go there and why we're actually missing one more part of this particular solution. Okay, now the first part of this particular solution here is knowing what Binomial Cdf talks about. Binomial Cdf talks about less than or equal to that number of successes. Again, wording is very important here. So if we talk about at least 16 to 20, so let's just focus on those words there, at least 16 to 20. That represents the successes from 16 to 20. So this is what you're looking at here inside your head. But what about the first 15 successes? Well, all I care about is what I want is I want 16 to 20. This is all I care about. Everything I care about is the one that's circled, 16, 17, 18, 19, 20. That's all I care about. I don't care about 1 to 15. I want to basically remove 1 to 15. I want to X it out altogether. So the question is, how do I do that? Well, the way I do that here is I have to add one more thing to the table, and that is using our rule of complements. I'm going to put 1 minus Binomial Cdf 20, 0.64, 15, and that will get rid of our first 15 cases. So, or actually this will be 0 to 15, but technically it'll still get rid of our first, up to 15 cases, and then we'll just have 16 to 20 left, and that's exactly what you're looking for when you see the words at least 16. Okay. So this is a bit tricky here. We're going to use the rule of complements when we see the words at least. And the only reason why we have to use the rule of complements here is because the fact that binomial CDF by itself is very restricted. Remember, it is extremely restricted to saying it's less than or equal to. So we don't have a choice in the matter. Okay, we can't go backwards here. Since binomial CDF by the calculator's definition is very strict and restrictive, we have to work within that restriction. And that's why I have to do 1 minus that binomial CDF here in order to make this work. Okay. So are there any questions about that? Are there any questions about that? Want to be sure that that's pretty clear here. No? Okay. Okay. All right, so we're going to enter this into the calculator here. Let's see exactly what we get here for our probability. All right. So let's do 1 minus. Okay, it's just you could just enter in the calculator here. 1 minus. Again, hit second and vars. I'm just going to scroll to Binomial Cdf, which is option B. Go ahead and put in our trials here. 20. Here 60.64. 15 here for our rid of those first cases. Paste that. And so here we get 0.1011. Okay. All right. So we have that there. That's again with at least 16 or at least some amount of successes. Let's put some more in. Yes, exactly, because it says at least. That's correct, Natty. So as we mentioned here, wording is one of those things. Again, if you're confused, Natty, and that's fair, that's definitely fair to say. If you're confused, draw out a picture just like I did here. Just draw out a picture of like your cases here. What do you want to keep and what do you want to get rid of? And how does that fit with the definition that we have here for, say, binomial CDF? Okay, because binomial CDF is one definition only that's less than or equal to. Okay, say I want to keep this because this is what I want to solve for, but I want to get rid of this. Okay, I want to get rid of this so that way I just have whatever I want left over. So that's fair. Okay, you definitely can do that. Let's try another one, okay? Let's try another one, and let's see how we can work with that, okay? Same numbers, just a different, maybe different question here. I'm going to try several more examples here for sure. Okay. All right. Try another one here. This one here may or may not be in the book. Label this as B anyway. All right. So this one here is my own made up one here. About the probability of less than 14. What's the probability of less than 14? How would you set up that problem? The probability of less than 14. I'll give you one thing right away. So one thing right away that I'll just give you right out the gate is we're going to use Binomial Cdf. We got to put some numbers in there. So what number should I put underneath the Binomial Cdf? What should that look like? Oh, very nice, Beth. I like that. Yes. Yes, that is correct. Very good. Absolutely 100% correct. Very nicely done, Beth. Very nicely done. So we have binomial CDF here, 20.64 and 13. Notice that this problem here specifically says less than 14. Okay, less than 14 meaning 14 is not included. The only cases that we want are the cases between 0 and 13. We don't want 14 in there because it's less than 14. If I said 14 or less, then okay. 14 or less is fine. 14 would be included. But if it says less than 14, 14 is not included. It's just 13. Okay. So I 100% agree with this. Absolutely. Right? Looking at that wording super carefully, we're able to come up with this conclusion right here. So let's go ahead and put this in the calculator here, actually. And let's see what we get here, right? Very nice, very nice. All right, like what happened here. Let's do, again, second and vars. PDF. I'm doing it the manual way for whatever. Okay. And so here we get 0.6197. All right. Very nice, very nice. Let's try another one. All right, I'm going to go all DJ Khaled up here. So do another one. Okay. Let's do the probability of more than 17. Probability of more than 17. All right, now why don't you guys tell me, how would I set up this problem here? This time I'm just going to be hands off here. We are going to use CDF, by the way, so that's not going to change. But you guys tell me, how would I write out that work for this problem here? Probability of more than 17. Okay. That's all right, Beth. I agree with everything except for one part. All right, so Natty and Beth, you're both really, really close. Like, really close. So I agree with everything up until a certain point. So numbers are correct here. At least the first two are. Not quite, Natty. You're skipping a number. That's right. By process of elimination. That's right. So it is 17, okay? Remember what this says here. This says more than 17. So the cases you want are 18 to 20, which means that all the other cases between 0 to 17 are things you want to nix out. You don't want those. You just want 18 to 20 here. And again, because they were restricted here, we do 1 minus and with the 17 included there. So you're close with the 16 there, but remember, this says more than 17. So 17 is not included. Okay, that's why we want to phrase it that way when we actually do this out. Okay, I understand. Totally understand. Again, problem C says less than 14, but think of it this way, Natty. We didn't include 14 in this last one when we said less than 14. If we say more than 17, well, doesn't that mean the same thing? We're not including 17, right? If you can, again, just draw out a picture of the numbers you want. It says less than 14. Okay, you say 0 to 13, right? That's what you want. You don't want anything else apart from 0 to 13. That's fine. So you've got to be very extra vigilant and very extra careful. But if you draw out what you want there, you can kind of get a good guess about where you want those numbers to be. All right, let's go with our 1 minus second bars. Go to probability of at least 16. Yes. So understand that at least and less than are not the same thing. So at least is not the same as less than. They are two different things. Two very different things, actually. At least is more than? No. Not true. At least is not more than. Two different things as well. Because at least includes one extra value, whereas more than does not. That's why. So just recapping what you've just said there. Again, at least includes one extra value. More than does not include one extra value. Tell you what, I'll write that down here in the for the replay value here. So let's. So you could say the words, at most includes one extra value, less than does not. Okay, if you want to put the opposite. All right. Yes. Oh yeah, right. Still have to put this in here. Yeah, no problem. Like I said, wording here is like super important. So that's why I want to take extra time and talk about it, because I know how difficult that can be, because that's the thing that we've been stressing since the beginning of chapter 5. Is exactly that reason why probabilities can be so confusing when you look at it from saying, oh, you think it goes one way, but it goes another way, and the reason is just that little technical detail in the wording there. All right. Okay. All right. So let's go ahead and figure what this out is. Let's do this here. We have 20.64 and 17 here. So let's do that. There we are. So here we get 0.0096. Okay, so that's what we get here for this. All right, there you are. That is letter E. All right, got one more part to do here. Okay, so this will be the last example here for today. But this one here is just as important as the others. So let's talk about this one here. So let's say we want to find the probability, and I'm going to change the numbers here from what the book says. So probability between 8 and 12. So this time here, we're taking a look at the probability between 8 and 12. All right? The probability between 8 and 12. So this one here is a bit tricky, but again, in order for us to find this particular probability, let's take a good look here at Binomial Cdf again and focus on just that less than or equal to part here for that number of successes. Okay? So if we look at that specifically here, this is less than or equal to that number of successes. Now, what does that mean here in this case? It means that we're going to have to do two binomial CDFs here, okay? Because what we're trying to do here is we're going to go first from 0 to 12, because we want 8, 9, 10, 11, 12. That's what we want, okay? We want 8, 9, 10, 11, 12. Those are the cases that we want to compute over. But we want to get rid of the first 7 cases, okay? So we go up to 12 cases, but then since we want 8 to 12 here, we want to get rid of 0 to 7 and 8 to 12. So we go up to 12 first, and then we get rid of the first 7 cases. So what we have here is we're going to have here, first of all, Binomial CDF. I have 20.64 and 12. Again, 12 meaning less than or equal to 12 according to the definition of Binomial CDF. And we're going to subtract that by running out of space here, so expand the space. So we're going to subtract that by, when we get to the space, I'll let you know. All right, I'm going to subtract that by Binomial CDF 20, comma, 0.64, comma, and in this case, we want to get rid of the first 7, so let's put 7 here as our guy. So this will essentially take care of everything between 8 and 12. The case is 8 to 12 here. Go up to the first 12 cases, and then get rid of the first 7. And now all we want to do now is just take this guy and put it into our calculator, and we're going to be able to solve for this easy peasy lemon squeezy. Let's go ahead and we're just going to do this twice. Okay, we're just going to do this twice. So hit second in vars, Binomial CDF. We have 20.64 and 12 for the first one. We'll hit subtract, second in vars again, Binomial CDF here again, 20.64, and then this time 7. There and paste it over. And then we'll just hit enter again to subtract the 2. And there we have it. We have our probability of 0.4282. Forgot it. There is a couple more things I got to do actually, but very quick. So very quick. I'll have a couple more things to do. But are there any questions about that example there? Any questions about that? Right. Hopefully this is making a whole lot more sense than it did, hopefully 5 minutes ago. All right. Okay. Yes, good. That I'm very happy to hear. At first when you do this, it's like, oof. But then when you start understanding how the wording and how the calculator kind of likes to do things, it starts to make a lot more sense. Yeah. Always oof when you start. All right. Now we do have one more question here on the handout, so let's at least acknowledge that here really quickly. So what they may ask you to find is they may ask you to find the mean and standard deviation and the variance here once again. Now fortunately for the binomial distribution, the mean and the standard deviation are very, very simple to do, because all you have to do is, for the mean, you just take the number of trials times the probability of success. Standard deviation, just take the square root of np times 1 minus p, and that's the standard deviation. It's just that easy. There is very little work that you actually have to do. Now, this stuff here is something that you do have to memorize here, so be sure you kind of write this one down. This one is open and fair game because of how easy it is to begin with. So in our case here, if we wanted to find the mean and standard deviation, and heck, even variance if you wanted to, it's very simple. Let's go ahead and do that here for this particular problem, and we'll see what we get. Okay, so calculations for this one here won't take us too long to do, so it'll be a quickie. All right. So what's the mean here in this case? Well, the mean here is equal to n times p. Well, what's n? N is the number of trials, which was 20. The probability of success here being 0.64. And all we have to do is multiply that on the calculator. I'll quickly do that here on my end. So 20 times 0.64. So here we get 12.8. So that's the mean there straight up. Next thing we have to do is doing the standard deviation. And if you do the standard deviation, and that's the square root of np times 1 minus p, drop the square root, you basically have the variance. So we do np times 1 minus p. Let's do that really quick. 20 times 0.64 times 1 minus 0.64. So all right, so our variance here, if you wanted to figure out before we get into the actual thing, our variance here is 4.608. So if we take the square root of 4.608, which will be our standard deviation, quick, we get 2.1466. All right, and there we have it. We have our standard deviation here for our example problem here, number 37. Okay. Oh, okay. Any questions any questions from section 6.2? Figuring one example would be good for this section here, considering how much involvement that there is. So hopefully this made it a little bit easier to go ahead and do. All right. Very good. Very, very good. Okay. So, if there are no more questions, I want to thank you all for coming on out here today. I really, really kindly appreciate the time that you guys have had. That you guys give me here every week. All right, you guys are well respected and well loved. I can guarantee you that. Thank you so, so, so very much. All right. Thank you all very, very much here. You guys, thank you. I don't even know how many times I can thank you guys. But I hope you all have a very wonderful weekend. All right. Hey, I always have time for your questions, Natty, at any point in time. All right. That's what I'm here to do. All right. I guarantee you that. All right. Thank you all so very, very much. Have a wonderful weekend. Remember, stay safe, stay healthy, and most importantly, everybody, stay sane. All right? Take care of yourself. Okay? That's okay, camera. Not a problem. As long as you're following along, that's all that matters. All right? Have yourself a wonderful night, everyone, and we will see you on Monday, continuing on with Chapter 7. All right? See you later, everybody. Take care of yourselves, and have a good one. All right. Bye.